So we've gone through motors and generators, and we've actually seen the pictures in motors and generators that if I have a DC circuit and the way it would pick up, and we actually showed these, that this would be kind of how the current would come through on a DC generator. But on an AC generator, we're going to get current come through like that. And so now, since we don't do DC generators, you do in your car, but we don't use those. We use AC in our outlets, and DC is going to be direct current in our circuits. We need to look at how our circuits respond to an AC signal. So let's start with a simple circuit. This is the circuit that we've been having for a while, and it's got a resistor in it. But now if I'm going to draw that circuit, I still have my resistor in it, and now we draw it with a little symbol that looks like that, and that shows that we get an AC circuit. Do what? Yeah, that's what I was worried about, because the heater's blowing in here today, and I can hear you guys. But this room has a tendency to do that. Is that better? Is that better? Yeah, I can hear you guys. Okay, all right. But just holler at me if we need something. Okay. All right, so we can get this. This is our circuit if we've got an AC circuit. So let's look at this. So since I don't draw really good diagrams, I pulled the diagrams out. So here's our good old circuit. Scroll in so we get better focus. There we go. And when I run an AC circuit, what you're going to end up seeing is I can follow, and I can put my voltmeter on the circuit, and I can put my amp meter in the circuit, and I can follow when the voltage hits maximum, and I can follow when the current hits maximum. The key here is that the voltage and the current are going to be at the same point in our sine wave. And remember, way back when, which is why I start with simple harmonic motion so that we can look at those sine waves, is because when we get over here to AC circuits, we're going to see those sine waves again. And now we see them again. But one of the key parts here is these two are what we call in phase with each other. They're going to be exactly following each other, and they're mirroring each other. They won't have the same values. One will be the maximum current, and one will be the maximum voltage. But we're going to follow the same pattern on the circuit. So we will actually follow that pattern. So what happens to us is we've got that lovely sine wave. And things that we remember about sine waves is that sine waves had a frequency times time. When it was back to our angular frequency times time. And I can rewrite that as 2 pi, our frequency, times time. Now, in the US, most of us know that our cycles on our AC circuits are 60 hertz. In the EU and other countries, their cycles are 60 hertz, which is one of the reasons why you have to have an adapter for your equipment to make sure that it all works. And that's what this frequency is when we put it into our sine wave equation. And remember, a hertz is a 1/2, since we haven't looked at it in a while. So what happens is, going back to our lovely diagram, is that my instantaneous voltage, which we're going to use as a little v, is going to look at, and we'll talk about it as the change in voltage, is going to look as the change in voltage max sine 2 pi my frequency times time. So we're going to start to see how that works. And we will end up looking at, so let's look at power. So we're going to go in here and we're going to talk about what we call the root mean square. Because essentially, if I'm running a hairdryer, or I'm running my toaster, or I'm running my refrigerator doesn't necessarily see this voltage. It's going to see more of an average voltage. We're going to look at an average voltage, we're going to look at an average current, and we're going to look at our piece of what's that current look like, and it turns out that it looks as the root mean square. So RMS stands for root mean square. And that's going to give us our instantaneous conversion and our instantaneous. So our power average, the average power that we get over time is the I squared max times the resistance in the circuit. My instantaneous power is going to be a script I squared. So we're going to use this script I for instantaneous. And we're going to use that script V for instantaneous. And we want to end up looking at the RMS value. So to look at that average, and basically we need to think of it as because these things are going to happen quickly. And we don't monitor these instantaneous things, we monitor the averages, and that average works out to be the root mean square is going to be my I max divided by the square root of 2, or it's going to end up being 0.070 I max. My root mean square of the voltage is going to do the same thing, max divided by the square root of 2 is going to give me my 0.707 voltage max. And my power average, just like I showed on that little slide, is going to be my RMS value, the average value of I, but we end up getting our the root mean square squared R. And what's happening to us is this, is if we're going to use the script as instantaneous, we're going to use the maximums with max, and then we're going to use the RMS values to give us those averages that we play with. So let's work a quick problem here. So 1, 2, 3, there we go. Trying to keep my slides straight. So we're going to use our regular circuit. So our household circuits are typically 110 volts at 60 hertz. And we're going to connect it to a resistor of 10 ohms. And we want to calculate the RMS voltage. We want to calculate the max voltage. We want to calculate the RMS current. And we're going to calculate power. So, clue here when you get these problems is to look at what they actually give you. We're told that we have a 110 volt circuit. That's my max power. Now, WebAssign, when you're working on your homework, might give you that my voltage, my little script voltage, is going to equal, let's do 220 sine 120 pi t. And it might ask you what the voltage max is from that. Remember, I can read it right off my equation, which is why we spend so much time with that back back when we did our simple harmonic motion, because that tells me that that's, oops, I wrote it down wrong, 220 volts. And in your house, you typically will have a couple of circuits that are 220 volts. If you have an electric dryer, it's on 220 volts. If you have an electric oven or stove, it's on 220 volts. And you can actually get different voltages. I have a heater air conditioner on a 220 volt circuit. Now, if I look at this, and this is kind of fun to think about. So let's take an aside here. If I've got my air conditioner has a special plug that looks like that. And you'll look at that plug, and our typical plugs look like this, right? Because we typically have, and it looks like this. That's a ground. But my 220, and actually a lot of times it'll have little dashes like that, so it's a special type of plug if I look on the wall and I see a roundish plug, these are typically, they're not always round. In Europe they are round, but in our convention they look kind of like this, right? That's what our typical plug outlet looks like. But I'll have a plug that looks like that. Now my dryer plug and my oven plug, first of all, they're a lot bigger. And I'll actually end up with a bigger plug, and I might get a plug that looks like this, something that looks like that. And that's telling me I've got a different kind of plug that I got to worry about. So you have to actually look, and there are actually two, for your dryers, when you buy a dryer, you actually have to buy a 220 pigtail. And that's what they're called. They're called pigtails. You have to buy a special 220 pigtail, and there's two styles, so it depends on what your house is wired with, which kind of style we have. And we're going to find out why none of these are ground in a 220. Okay? None of those are ground in a 220, whereas my 110 has a ground. These are set up differently. The ground is there, but the plug itself is set up differently, and we're about to find out why. So just a little aside. So what we want to do, so we've got Vmax, because we can read Vmax right out of the problem, or we can read it right off of the wave equation that they give us. My Vrms then is just going to be my Vmax divided by the square root of 2, which is going to give us 77.8 volts. And we're going to see that again, because I'm going to use regular household circuits for a couple of my examples that we've got going. So we're going to see that 77.8 again. Now I have to calculate my my root mean square voltage. I've got my circuit. So remember that V is equal to IR. And I can do I is equal to V divided by R. So if I want to do a root mean square current, I can also just use a root mean square voltage. And so I can take my 77.8 divided by my 10 ohms, and I get a root mean square of 0.778 amps. Now I can calculate power. Power is going to be I squared over R, or times R, and I'll put my 7.78 amps squared times my resistance, which was 10 ohms, and I'll end up with 605 watts. So these problems aren't terribly difficult. We just have got to use a little bit of different terminology. So we looked at, remember, we got three components. We have resistors, we have capacitors, and we have inductors. And we already saw that there was a time dependence here. And we saw that there was a time dependence here. So now let's look at my circuit with my just by itself with a capacitor. So I'm going to do this. I'm going to get my handy dandy little chart out. And if I have my current set up, my little amp meter in my system, and I have my little voltmeter in my system, as the current goes through, I've got my nice 60 hertz or my 50 hertz current. The voltage takes a little time to catch up. And it turns out that we're 90 degrees out of phase with my current. And my capacitor turns out to lag the current. It's said to lag the current. It takes, and if you think about it, what's happening in the capacitor, remember I'm getting the little charges in the electrons, and the electrons are charging up my capacitor. And it's not until it gets charged up that I'm going to be able to have circuit flow through it. So it's going to take a little time to fill up my capacitor. And then now the current's getting shut off. Now it's going to bleed off, and I'm going to end up being behind my current. My current's going to end up being behind. So it's said to lag. So if we think about that lag, what we're seeing is that the current and the voltage are out of phase with each other. It's going to lag. So what we need to do in order to understand how these currents work is we need something to account for the delay. And we're going to define something called reactance. And we talk about that, we're going to give it an X, and we're going to put a little C here because this is going to be the reactance associated with a capacitor. And by definition, because we can play with it and look at that phase, by definition, we end up with 1 over 2 pi times the frequency times whatever my capacitor is. That's going to give us the reactance. And it turns out this reactance is going to be like a resistance in my circuit. So it's going to be in units of ohms. We're actually going to see it in units of ohms. And you can kind of think of this empirically because basically that's what it is. It's an empirical way to do it. So we can rewrite Ohm's law for capacitors. And we'll get the change in voltage is equal to the current, RMS, times the reactance associated with my capacitor. And then the problems are going to work pretty much the same way. So we're going to calculate the reactance of so I'm going to start here. Oh, if you want a fun one, my column this next week is on dying of Easter eggs. So I did my research, and if you want to have some fun, if you've got turmeric in your spice cabinet, it'll give you yellow. And if you've got cabbage, red cabbage, it'll give you a nice pretty blue, provided that you make sure you've got your vinegar in there. And beet juice gets you a nice pretty red. So you don't have to go buy the little tablets if you don't want to. And everybody know why the dye why you have to have vinegar in to dye your eggs? Well, it doesn't really soften the shell, but it does something to the shell. Shell is primarily calcium carbonate. And you all have you've all been through chemistry, right? Remember in the reactions, one, there was one that you had to do a 2-part reaction because you mixed the calcium carbonate probably with HCl, okay? You mixed it with HCl, and what would happen is you would get a calcium chloride. Calcium's 2, so you get a calcium chloride, and then you would get H2O plus CO2, and the CO2 would bubble off as gas. Well, what happens in your Easter eggs, so let's take, I have that little red pellet that I got, that little red pellet. It's a sodium, whatever the color anion is. Whatever that color anion is there. And what's going to happen to us when we put that and disassociate it in our water, we want to make sure we have lots of extra lovely little hydrogen protons floating around in order to get this reaction to go on the shell. And what will happen is the hydrogen's more reactive than the sodium, so the color is going to attach to the hydrogen, and when I produce that reaction, it's going to do just like that, making that calcium chloride salt, except now I get a calcium color salt on the eggshell. And that's why you have to have that little bit of extra acid in there, and the more acid that you put in, the deeper the color, because you'll get more reactions. So that's the fun part. So if you're dyeing Easter eggs this weekend, now you can explain the chemistry behind Easter eggs, and then you can tell your family you learned something, right? Don't tell them you learned it in physics class. But hey. So we're going to calculate the reactants. For a circuit with a 10 microfarad capacitor and the current RMS for a 60 hertz 110 circuit. I mean, we might as well work practical problems, right? So we know what the voltage max is. It's 110. We know what the voltage RMS is, because we've already done it. We've already calculated it. It's 110 divided by the square root of 2, which is going to give us 77.8 volts. We want to calculate the reactance, and that's going to be 1 over 2 pi, my frequency, which is 60 hertz, and 10 times 10 to the minus 6, because I've got microfarads, and my units end up in ohms. I know that seems a little weird, but that's what happens. And then I get 265 ohms if I plug that into the calculator. Now I get my current RMS is going to equal my voltage RMS divided by the reactance. And that's going to give me my 77.8 volts divided by 265 ohms. It's going to give me 0.293 amps. So we can go in and do these calculations. Well, we got one more circuit. This time we've got our inductor. Now when I do the inductor, it turns out that if I'm following current, remember, inductance is a resistance to change resistance to the change in the current. So the inductor is resisting change in the current. So it turns out that my voltage is going to lead the current by 90 degrees. So my inductor is going to lead the current by 90 degrees. My capacitor lags the current by 90 degrees, and my resistor is in sync with the current. So we end up with those pieces. So we'll come back to that here, so that we end up with that one. So we're going to develop a reactance for my inductor, just like we developed a reactance for my capacitor. And that reactance turns out it's going to be 2 pi frequency times my inductor. And I can rewrite Ohm's law the same way as I've done before. and I get an equation that looks like that. So we can do a problem just like we've done the last two. I can calculate the reactance for a circuit with a 30 millihenry inductor. And we're at a 110, 60 hertz circuit. And we want to calculate the current. So 110, 60 hertz, we know what that is. VRMS is going to be Vmax divided by the square root of 2. And we've done it a few times already. So we got that part. I got to calculate my inductance. And I got millihenries, so it's going to be 30 times 10 to the minus 3. And when I plug that into the calculator, I get 11.3 ohms. So my IRMS is equal to 77.8, 11.3, 6.88 amps, if I plug that into the calculator. Okay, so if I have a circuit that has just an inductor in it, the inductor is going to resist the change in current. If I have a circuit with a capacitor in it, the capacitor's got to kind of fill up and then it discharges. But a resistor is going to act instantaneously. So now I can put these circuits together and we've got things that are happening. So if I put the resistor in here and the inductor and the capacitor, and I'm following current, the resistor is right on top. My inductor leads, my capacitor lags, and I'm going to end up with something that's going to be dependent upon all three components. When I have larger electronic equipment, and I'm going to my 220 volt outlets, I worry about things that are in phase and out of phase. And it becomes a very bad day at the refinery because big pieces of equipment are built to handle the three phases. Okay? They're built to handle the three phases. And motors are actually, big motors are actually wound so that they can get the three phases. So we had a power outage at the refinery that I was at in Salt Lake City, and it browned out, but turns out what happened was we only lost one of the phases. So I don't know which phase we lost, but we lost only one of the phases, and these things have to work together. We had to rewire every motor in the plant because we blew them all out. It was not a good day. It's a very bad day. You don't like power going off at a refinery. Not a good day. Unfun. So understanding the fact that we have three phases in our AC electrical systems is a big deal. It's a big, big deal. And that's why you have those three-prong plugs for your 220s, is because now those bigger pieces of equipment have to adjust for those phases. So what happens to us is that we end up taking those three reactances, okay? We end up taking those three reactances. And the change in voltage that we see based on having those three components is going to be related to what happens with the resistor plus whatever lead versus lag that I get associated with the inductors and the oops, that's not a C, that should be a C, not an R, with the inductors and the capacitors. And this should start to look very familiar. Remember, a squared plus b squared is equal to c squared. And we talk about vectors and vector components. This starts to be able to be explained by a vector. And we can actually talk about a phase angle associated with our system as this change in my voltage that's related to my lead and lag divided by the change that's related to my resistor. This is called, this phi is going to be my phase angle. And we can start drawing what we call phasor diagrams. So those guys that are actually going to be electricians and those guys that are doing electrical technology, they're going to play with these things called phasor diagrams. Now, we've got that in terms of voltages, but that doesn't really help us because one of the things that we did way back when is we calculated the effective resistance of a circuit. We calculated the effective capacitance of a circuit. We didn't necessarily calculate the effective impedance of a circuit, but you probably could. We just didn't do it. But we did do that effective resistance and we did do that effective capacitance. So what we end up doing is we end up defining something that gives us an effective behavior of our circuit, and we call that an impedance. And we give it a lovely letter Z to do it. And my impedance is going to be defined as the resistance squared plus XL minus XC squared. And my phase angle in this case is going to be my XL minus my XC divided by R. So we're going to give that circuit a behavior based on what my equivalent resistance is, and the impedance or the reactance associated with my inductors and the reactance associated with my capacitors, so that I can look at my phase angles. So if you pick up a circuit book or you pick up or go start looking on the web or something like that, you might see phasor diagrams that look like this. That we've got our impedance, and I've got my lovely little vector diagrams that relate to how the phases are interacting with each other to have my equipment operate. Now, for most of our little electronics, we don't have to worry about this because we're not talking about big changes to the system. But for our big electronics, those things that are big motors, the big electric motors, your dryers, your stoves, all of those things, we got to worry about how the system is put together and what the effective impedance is for the system. So we can actually look at that. The other part about this is I can rewrite my Ohm's law for this, that my voltage max is going to equal the impedance times my current max. So I can look at Ohm's law for the whole system and be able to look at that piece. So let's kind of work a problem here. Okay. All right. We're going to be given a circuit with a 300 ohm resistor, a 0.9 Henry inductor, 3.5 microfarad capacitor. We're going to use our typical 110 circuit, and it's going to have our typical frequency of 60 hertz. We want to find the impedance, the maximum current, and the phase angle. Okay, we're going to find the impedance, maximum current, and the phase angle. So we just defined impedance as R squared plus XL minus XC squared, and our phase angle as XL minus XC over R, and my voltage max is going to equal I Z. So my max current is going to equal my voltage max divided by Z. So to do the problem, I have to know what XL is equal to, and I have to know what XC is equal to, my reactance associated with my inductor, and my reactance associated with my capacitor. XL we had defined as 2 pi frequency times the inductance. So that's 2 pi times 60 hertz times 0.9 henries. If I plug that into the calculator, I got 339 ohms. My XC is going to be 1 over 2 pi times my capacitance. And I get 1 over 2 pi 60. Capacitance in this case was 3.5 times 10 to the minus 6 farads. If I plug that into the calculator, I get 758 ohms. So now I can plug that in to Z. It's going to be the square root, and we're told that we had a 300 ohm resistor. My XL was 339 minus 758 squared. When I plug that into the calculator, I get 515 ohms. So I can quickly do Imax. Right? Imax is going to equal my 110 volts divided by 515 ohms. And that's going to give me 0.2136 amps, or approximately 2.214 amps. And I can do my phase angle. It's going to be my 339 minus 758 divided by 300. Plug that in the calculator, get a minus 0.140. So, oops, I'm used to writing theta for my angle. Gives us a negative 54.3 degrees. And for you medical types, you probably aren't going to run into these things too much. unless you're like me and remodeling a house and they're having to deal with circuit diagrams in my house. I had to deal with my 220 circuit for my new heating and air conditioner. And I've been reinstalling lights and putting in fans in the ceiling. So yeah, we've been having fun with electricity. But luckily, I haven't had to deal with phasor diagrams because I haven't had to move my 220 circuit yet. I will. I'm moving my washer and dryer hookups to someplace else. So I got to move those around. And I did talk to you guys about the traffic signals, car traffic signals. I didn't talk to you guys about the car traffic signals. Well, let's talk about that real quick. It's got a little bit of time. So you go to a stoplight, and there's a cut in the road at the stop sign or at the traffic light. If you think about your car is a big chunk of steel. It's got magnets in it, right? It's got magnets in it. It's got electrical in it. This right here, if that's a chunk of wire and I drive across, I got a changing field. And that creates a signal to the traffic light to let you know that there's a car there. So that goes back to my inductors. So you end up with inductors. Okay, so just to kind of look at the elements. Ew, that one's a little tough in here. But that's a little better. So I've got a resistor. My phase angle is going to be 0. I've got a capacitor, and my phase angle is going to be minus 90. It's going to be out of phase. It lags. My inductor, my phase angle is going to be plus 90 because it leads. But if I have just a resistor and a capacitor, I'm going to have a situation that looks like this. If I have a resistor and an inductor, I'm going to have something that looks like this. And then I'm going to have all three, and I can do the combinations. So that kind of gives you a summary of where we're at. So that, what? Oh yeah, it should be a round table. These slides were from the previous edition of the book, so I'm not 100% sure that table 21.2 is going to be table 21.2 in this edition. But all of these figures that I've shown so far today are in the book. And I don't know if the current edition of the book, right after it does this, it actually shows you how the metal detectors work in the airports and public buildings and all of those things, because it works off of, let's go back and let's look at this. Let's go back here. Well, I don't have those on there. But if I look at my inductors and my capacitors, right, we have the inductor. The inductor is 2 pi frequency times my impedance. Okay, I've got that's my reactance of an inductor. And my reactance of a capacitor is 1 over 2 pi the frequency of the capacitor. So if I have a device here, okay, I have a device there, and if I put a piece of metal through that device, which is why it's metal, it's a metal detector, this frequency associated with this device is going to be set. But if I put a piece of metal through there, think of putting, my inductor, typically is a magnet, right? I probably have magnets set up in here that the magnet is going to create a magnet or electric field in my piece of metal that I'm taking through. And that electric field is going to create a magnetic field, And what's going to happen is I'm going to disrupt that frequency. And we talk about, and we saw that in pendulums, right? We saw that in pendulums, that if I have a pendulum, or we saw it in sound tubes, I can get nice standing waves. But if I was a little off, I got beats, right? I got beats, or I got a disruption in my standing wave pattern, and that's what's happening here. I'm going to get a disruption. I'm going to upset the resonant frequency of this device if I carry a piece of metal through. So that's how those lovely things work. And your book actually goes into a lot more detail about it. All right, so we're going to talk about one more thing, and that's where I'm going to quit today. Because if we start talking about Maxwell after we do these things, it just blows minds. It just blows minds. So we don't want to do that. So we've talked about the fact that I have high voltage power lines, right? I'm going to move out. We've talked about that I have high voltage power lines. And my power lines we've talked about can be as great as 115 it starts at about 115 kilovolts. Typically in the US, we're at 500 kilovolts across the high voltage power lines. And the reason is that we want to be there is because power goes as I squared over R, and we want to, or if I look at it the other way, power goes, did I not write it down? I didn't write it down. But power can also go as I change in voltage. Okay, so I can look at these powers change in voltage, and to minimize power losses over long distances, we want to be at a higher voltage, which is one of the things that we got to do. So one of the things that happens in our system here is I've got my power generation here, and I got to step it, what we call stepping up. The voltage to get to my high voltage power line, but then I come down and I have to step down. Because I don't use 500 kilovolts in my house. Right? We've been saying we do something like 110 volts in my house. I might have a 220 volt system. But I got a problem in that if I've got these high voltage power lines, I got to get the voltage up. The windmills have to generate those voltages, and I have to be stepped up, and then I have to have them step down. Now, one of the things that we saw, good old Faraday, he showed us that we could do some things with these magnets that I could, depending on how I, here I've got something in here, I can actually step up or step down depending on what kind of solenoids I have on my bar that I have in there. And you've actually probably seen transformers, you just don't necessarily know about it, because I actually have small transformers that are around. You get a lot of transformers that are there. They usually look like something like this. If I have an old one that was in the back of the TV, you had this thing that had some kind of lump here, and then you had these little pieces that went around it, and these had little fins on it, and it was kind of gray. You usually saw them, they were little gray devices. And you've seen bigger transformers around, right? The bigger ones, they usually have something that looks like this, and they've got fins on them. Basically, they have a big, large piece of iron that I can make an electromagnet out of, and I can step down and move it back and forth. So I can step up or step down, okay? So I can do it every which way. And how you look at these systems, you get a transformer equation that looks like this. So my change in voltage, and we saw this already, so my change in voltage is going to equal, because we've talked about solenoids, my change in flux, just like that, right? We've seen that equation. That was the solenoid equation that we had. We've seen it around. But if I'm connected to the same piece of wire, okay, if I'm connected to the same piece of wire, or same piece of iron, this is the other side. Okay, that's totally the other side. Well, my change in magnetic flux is the same for both of these. So let's go ahead and do this. Now I don't have to worry about my change in magnetic flux anymore. Because now I can just set this up as where N is the number of turns. Where N is the number of turns. So I can set this up as this way. And if my change in voltage 2 is greater than the change in voltage 1, this is considered to be a step up. And my change in voltage 2 is less than my change in voltage 1, that's a step down. And then for an ideal transformer, I get the current and this is for an ideal transformer. And you guys have worked with these kinds of problems before. Molarity being one. You know, you can look at those. And you can look at power losses associated with transformers. You can look at what the differences are in power losses. But that's where, those are our transformer equations. This gets us about 2/3 of chapter 21. What we're going to do when we come back on Wednesday is we'll talk about Maxwell's predictions, because Maxwell kind of pulled everything together. And we'll start and we'll look at a little bit of antennas out there, just to get to a little bit of antennas, and then we'll hit electromagnetic waves, and then we get to start optics. So that's going to put us to a point like next Friday that I'll go ahead and get a quiz out, and we'll probably go ahead and do a take-home test next Friday, which would be the 19th, on this last little bit of magnetism and things like that, so that we can just be focused on optics at that point. So we're good. We're getting down to the end of the semester. Woohoo!